Hi guys, this is the just in case video. I'm hoping to teach you this lesson in person, but if my fetus decides to see planet Earth before then here's the video. So this is the video for just in case for Tuesday, November 9th or Wednesday, November 10th, depending on if it's an A day or a B day. So what we're going to do today is notes 24 on BSEPR, which is usually pronounced Vesper. And then we're going to finish up the homework 4.4 that we potentially started last time. So today what you're going to need, you're for sure going to need these cutouts, this cutout here and this cutout here. Don't worry about this one, not using that one, but when you cut this out, I would recommend, let me show you like a brief kind of what we're doing from last year's notebook so you can see. I would keep them together. See how like I've got them together and together. Don't cut them out individually or you're going to have a really hard time. You're also going to want to grab just some colors so you can color code a little bit, but otherwise I'll go through the notes with you. So pause the video so you can cut these out. So once we'll see, this is kind of how you're going to tape it on your page or glue it. I've got the title at the top, BSEPR, Vesper, and the first glue in, and then the second one. Let's see. I do want to make some modifications before we start. The picture down here never prints as good as I want it to. So zooming into the bottom, kind of pay close attention to what I'm doing. There are some areas that have lone pairs of electrons and they had a really difficult time printing. So like here, we've got 1, 2, 3 atoms coming off of the central molecule. And here, one of them has been replaced with a lone pair. Look up here, see how this is a bond and this is a lone pair, but it's hard to see. So you need to actually darken up those dots that are there. So there's a pair of dots here. And then looking at this set of pictures, let me actually, if you have a Sharpie or something, or just a thick marker, let's really draw the distinctions between the columns here. This will make a lot more sense because see, now we've got 1, 2, 3, 4 things coming off the central molecule. This has 4, this one had 3, but now the top one, look up here, the top bond has been replaced with a lone pair. And I'll explain this again more in a minute, but we need to just make sure that the lone pairs are actually visible in your notes. So let me put all of them in so you can see, you can kind of still see them on your paper, but they're not the clearest thing in the world. So I want to make sure that everyone's got them. So there they are. And to make it a little bit more clear what's going on, I'm actually going to put the lone pair in this like light purple color so that it's even still a little bit easier to see. For aesthetic, I'm going to just do the little bubble thing around it. I'd recommend that you do the same with your pencil. right? So that's what I'm looking at. And then additionally, take a moment, pick whatever color you want for the central atom. I think I'm going to go with red, no reason. And for all of the pictures, color code the central atom red. And then when you're done with that, you'll want to pick a new color, and all of the other stuff that's attached to the middle, you'll want to do it in that separate color. In my case, I'm doing yellow. As you're coloring, start to notice a pattern. This first one is a central atom that's attached to two things, 1, 2. This next one is attached to 1, 2, 3. 1, 2, 3, 4. The next one, 1, 2, 3, 4, 5. I got to go back and color the middle. 1, 2, 3, 4, 5, 6. On the top now, we've kind of figured out the pattern here. Here we have, this is the base shape. This is the base when two things are attached. 3 things, 4 things, 5, 6. And then we're going to call this our base shape. And there's our base shape column. Underneath that, the first row, I'm just going to keep going through and coloring, and hopefully you're coloring along, keeping up. If not, pause the video so you can catch up. But now in the second one, I'm noticing like it starts out, similar. I have a central molecule, a central atom on each of the molecules. I'm coloring it. And I still have in this one, I still have 3 things attached to the central molecule. I've got 1, boop, 2, boop, 3, the lone pair. It still has 3 things attached, but one of the sides has been replaced with a lone pair. In this next column, base shape 4, we still have 4 things, 1, 2, 3, 4, just that the 4th one is a lone pair. So this whole column, this whole row, rows go side to side. This could be described as what happens when you have 1 lone pair of electrons. It's the base shape, but it got modified so that one of them is a lone pair. And here's the base 6 with a lone pair. Once you've seen that, the next row becomes really obvious what's going on here. Same base shape, but now we have 2 lone pairs of electrons. So on this one that I'm coloring right now, look up here. It has 4 groups around it. 1, 2, 3, 4. These 2 dots, these ones, have been the same each time. We just have been slowly replacing them. All right, so I'm gonna go pretty quick here. You kind of, I'm hoping, get the vibe, and I'm getting a little bit redundant. But color this through. The last one, obviously down at the bottom, will be what happens when you have 3 lone pairs of electrons. Okay, so pause this video if you need to get caught up. Otherwise, I will keep talking because I am done. So these are the shapes, and you're wondering, like, why are we dealing with shapes? These are actually the shapes that molecules make. You guys are very used to just drawing blobs together willy-nilly, however you want. And I've been so far saying, like, yep, that's acceptable. But now we're going to start to look at, let me scoot up my paper. We're going to start to look at your willy-nilly connections and make them into real shapes. What I mean by that is when you draw CH4, we did that one on the homework the other day. We used the atomic tiles. I can hurry and make a CH4. I've got HH, CH, I need one more H, H. Boop, 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 boop. There we go, I'm gone. Okay, look up here. When I use my atomic tiles and I do carbon, hydrogen, 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 it looks like it's in a cross shape like this. It looks like it's flat and it seems like I'm making a cross, but that's not actually how the molecule is. The molecule isn't this tiny, like, flat cross looking thing. There's a really cool website. Let me pull it up for you. It is called MolView, M-O-L, like molecule, MolView. Here's the website, MolView, MOLView.org. And what it does is it takes this kind of flat picture on the left. This is the Lewis structure. The Lewis structure is just how everything is connected with lines. Vesper is another way of looking at molecules, and this one is actually dealing with, like, how are the 3D molecule, what is the shape? So over here, it kind of shows more realistically 3D, what is it? So if I type in CH4, which I'm not sure if that'll come up, I might have to type in the real name. Oh no, it worked. Okay, so I've got CH4. Let me see, can I get this on the center of the screen? Ta-da. Okay, so here's CH4. It looks like a cross. It looks like what we had in the notebook, just a cross. But the molecule itself, look over here. It's not a cross at all. It is not flat. It is not a cross. Look, I can even spin it. That's actually really cool. So let me get my face out of the way. Check this out. I can spin this molecule with my mouse, and you can see it actually looks like one of my dog's toys, where it's got, like, the base pyramid on bottom and then, like, that piece sticking out the top. And he really likes it because he can push on the top part like this, like, boop, and push it over, and it still, like, stands up, and then it has a new top part, and then he's like, boop, and then, like, now there's a new top part, and, like, boop. So this is how the molecule looks, even though we drew it kind of weird, like looking like a cross. So this is the difference between, we've got Lewis on this side, and then Vesper is the actual 3D one over here. So let me do another molecule, see if I can pull one up for you. Like in the notebook, the next one is PF5. I don't know if it'll come up or if I'm gonna have to draw it. PF5, here we go. So on my Lewis structure here, it's just a P with 1, 2, 3, 4, 5 things connected. But it's not like a flat, it's a 3D molecule, and it looks like this. Check it out. Let me zoom in, and let me try and make it look like your notebook does. So switch my camera so I can point at the notebook. See right here? This is the Lewis structure. And then up here, this is what I'm trying to show here. Yeah? So even though it kind of is just looking like a big star, it's not a star at all. Like it's not just those 5 points together. All right, let's see. Camera back on. So here are the shapes, and these are the shapes of the molecules. And we need to not only know what is the base shape, but what is the shape when one side turns into a lone pair. And that's what the chart on the bottom is. So last one, let me show you the SF6 molecule. It's sulfur hexafluoride with 1, 2, 3, 4, 5, 6 bonds. Over here, it kind of looks like it would be one of those like the Jack toys that you spin and then something with a bouncy ball, and I don't know how to play. But there's our shape. Okay, so back to the notebook now. Hopefully that visual was good. So VESPR, we haven't even talked about what VESPR is. VESPR is an abbreviation. It stands for valence shell. So VSE, valence shell electron pair. I'm running out of room. Repulsion. VSEPR, valence shell electron pair repulsion. It's the idea that these groups are going to repulse each other. They're trying to spread out as much as possible. That's all that's saying. That the electron pairs are moving around in the outermost shell, trying to get as much space as possible. So up here, this would be the shape. This is our, let's see, same as down below. This is our base shape when we have 2 things attached. Central atom with 1, 2 connections. An example would be BeF2, that's this molecule. An example here would be BF3, 1 in the center. And this one is kind of interesting. This one is actually flat, like a fidget spinner. You could whoop, spin it around. And I'm just going to go through writing out the formulas. CH4. Example, these were the ones I did just a minute ago on MolView. PF5 and SF6. I like the 5 shape. It's actually my favorite one because what it combines, it's a little bit difficult to see. I'll try and shade it in so you can see it. But like, see here how we've got this fidget spinner laying flat. Fidget spinner laying flat. That's still happening in the middle. And then we took the straight line component of this piece and also added it in. So the 5 is actually my favorite one because it has the components of the 3, and then it also has the components of the 2 shape added in. 2, 3, 4, 5, 6. And I don't remember, I'm having a hard time remembering which one is the one from like from the Sims game. If you like connect all the sides, it makes that like plumb bob shape thing. Like, do you know what I mean? Like, look, if I connect the base like this, square base instead of a triangle base, and then connect up the sides, shade it. See how it kind of looks like that thing that the Sims wear on top of their heads? Last minute Halloween. Oh, I guess no. I guess not. I guess if you're watching this, it's past Halloween. I was gonna say, just put one of those on your head and you've got a Sims costume. I just don't remember if it has if the thing on the Sims head is the triangle. Like, see how the 5 shape has a triangle in the middle that goes up 1, 2, 3. I think that one is the actual one. I don't think it's the square base. But there's the difference between the 5 and the 6. One of them has the triangular center and the other has the square center. All right, now here's the hard part. All of these shapes have a name and we've got to learn them. Look. So while Lewis structures focus on how the atoms are connected, Vesper, the one we're doing today, focuses on the actual molecular shape. This is super important because like with medications in biology, your shape, aka like your structure is what they call it in college lingo, but your shape determines the function. The reason that certain drug molecules work is because they have a specific shape that allows them to bind with your body. It's like how a key fits into a lock. The key has to have the right shape to open the lock. The molecule has to have the right shape to do some function in your body. These are the base shapes of all molecules, the really common organic ones. So here are the names. You ready? Pause the video if you're not ready, but here are the names. So the first one here, let me get a brand new color marker. The first one here, see how visually this is in like a straight line, all 3 molecules, boop, 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 straight line. We're gonna call this linear. Oh, line R. linear. This is a linear molecule. This one, it's kind of like got three sides. If you connected them, it would be a triangle. So we're going to change that a little bit. We're going to say trigonal. And since it's flat, we're going to call it trigonal planar. It is a flat triangle, trigonal planar. If we take off one of the sides, so we can't see it anymore, it's still there. It's still there. That side is still existing, but lone pairs are invisible. So when I'm looking at the molecule head on, I'm not actually seeing this side, but it's still there. 3 with one invisible side is not the same thing as 2. Let me say that again. Look up here. Look up here. Look. 3 with an invisible side is not the same thing as 2. 2 is a straight line. 3 with an invisible side is called bent. That was the scientific name that they came up with here. And if you're wondering how bent, the degrees that it is, this is just additional information. It's about 120 degrees between the yellow angle. Next one, 4 components. There's a game that has blocks that fall in patterns of 4, right? You know what I'm talking about? There's the block that has 4 that come together like this, or 4 that come together like this, or like, this is hard, this. Dun, 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 dun. And every single block is a variation of 4 pieces. And you're like, okay, what does Tetris have to do with anything? But tetra means 4. So this shape is called a tetrahedral. I should have written it below so I didn't cut off my molecule, but I did. So that's kind of sad. Tetrahedral, and when we make one side invisible, this is now a trigonal pyramidal. Four with one side invisible is not the same as 3, because this is popped up into a pyramid shape, and this one is flat. Moving on, actually, nope, sorry, I skipped this one. This one is also called bent when you have 4 with 2 sides invisible. This one is bent at about a 109 degree angle. They do have the same name though, but see, this one's way more squishy. The 5th one is called trigonal bipyramidal. Trigonal because there's that middle triangle. Bipyramid because you've got the top pyramid going up and the bottom pyramid going down. So this shape is trigonal bipyramidal. The next one here is called seesaw, where it's like got a straight component and then a little V shape. If you turned it sideways, it'd be like a seesaw, like teeter totter. Like 2 kids could like sit on this and go back and forth. Seesaw, this one where it's got a flat side and then another side that sticks out at 90 degrees there. That would be a right angle. Boop. Not that it matters. This one is called T-shape. really original with the name T-shape. And this one again, even though it has 3 invisible portions, we see a straight line. This would be linear to us. The shape is still got the base trigonal bipyramidal, but it looks linear because 3 sides are invisible. This one is called an octahedral. And I know you're like, wait, octa? Octa means 8, and this is 6. You are absolutely correct. But when you look at the shape up here, we've got 1, 2, 3, 4. There's 4 sides on that top pyramid. And then there would be 1, 2, 3, 4 sides on the bottom. So even though there's 6 connector atoms, they call it an octahedral because it has 8 sides. I kind of hate it too. If you want, you can also call this one square bipyramidal. I actually prefer this one myself because if this one is trigonal bipyramidal, that makes sense to me because the middle is a triangle. Square bipyramidal makes sense to me because the middle of this one is a square. So I like to call this one square bipyramidal, but I'll use both so that you can decide what you like. If this is square bipyramidal though, because I've got the top pyramid going up and the bottom pyramid going down, if I made the bottom invisible and all I could see was the kind of top pyramid there, right? This is called square pyramidal. Not bipyramidal, there's only one pyramid. So square pyramidal, because it goes just one direction up. And if you do this one, it would be down as well. And the last one would just make a square if you connected all of the sides, and it would be flat. This one is called square planar. The word planar is flat in our scientific lingo. Okay, pause the video if you need, but that is the end of the notes. Keep this open while you pull out, let's see, let me check what you need to pull out. All right, the paper that you're going to pull out is going to be 4.4. We did the back last time, and 4.4 front should now look a little bit more familiar with what we've got going on. So here are the shapes that we were just drawing. They should look very, very similar. What the difference is that you're noticing that some of the lines are regular lines, some are black and some are light. It does not matter at all between those. Those are just the artist trying to show like this one's coming towards you and this one is like kind of pushing away from you. And it's just a visual like aesthetic thing, but it doesn't actually affect our molecule. We still have the central molecule. We still have the center one. And in this case, we've got 1, 2, 3, 4, 5, just regular bonds attaching. The dopey little bubbles here are trying to show you your lone pair and your lone pair. I'm not saying you have to color this, but I'm going to color at least these two so you can see the difference between it's just the artist's depiction. Every textbook tries to jazz it up a little bit. So keep that in mind as you go through. And what we're trying to do is figure out what is the E and the M for each of these. What I mean by E and M are the following. E is the electron geometry, aka what is the base shape? What is the base shape with all sides included? Let's see, shape that includes all, I don't know, I'm not gonna say all, I'm gonna say shape that includes E for everything. That's the base shape. The molecular geometry is going to be the shape that you can see, because lone pairs are invisible. They're still there, they still take up space, but they're like little ghosts, little poltergeists. They're still a part of the shape, they're still there, but we can't see them. So when you have a shape like this, where there is no lone pairs on the central atom, none at all. It's got 5 bonds and no lone pairs. When there's no lone pairs, your E and your M are the same. 1, 2, 3, 4, 5. 5 things is called trigonal bipyramidal. Trigonal bipyramidal. Since there's no lone pairs, my base shape is my molecule shape as well. So I'm just going to write same. On this other one that I colored, I've got 1, 2, 3, 4, 5 things attached. My base shape is 5, which is called trigonal bipyramidal, same as this one. I should have written that abbreviated, but that's okay. My base shape is 1, 2, 3, 4, 5 things. But with 2 lone pairs, the molecule is, you watching? I bring it down, boop, boop. This one, my molecule matches T shape. So what about this one over here? I have the central atom. The central atom is connected to 1, 2, 3, 4, 5, 6 things total, 6 connections. I look in my notes, what's the name of a base shape 6? I can use the word octahedral or square bipyramidal. I'm going to go with square bipyramidal. The molecule, though, is whoop, square pyramidal. The only time that you will have the same E as your M is when there are no lone pairs on the central atom. So like this one, where it's just bond, 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 bond. All of them are bonds and none of them are lone pairs. That means that whatever you write for your E, your base shape of everything. It will be the same because there's no lone pairs on the central atom. That's the case when they're the same. All right, so finish up the front, fill in the molecules, and check your answers with the sub to make sure you've got those correct. And the back side gets a little bit trickier because now we're going to take the molecules that you drew the other day and try and give them like the same kind of names. So let me show you what I mean here. So at the bottom, we've got some molecules like ammonium. Well, here's the central atom. It has 3 atoms connected to it, 1, 2, 3, and it has 1 lone pair. So in total, it's connected to 4 things, 1, 2, 3, 4. I check my notes. The name of shape 4 is a tetrahedral. But since it has a lone pair, the molecule will be trigonal pyramidal. So same as on the front, except for now, you've actually got real molecules that you're working with. So next one, water. Here's water right above. Central atom is oxygen. I have 2 bonds and 2 lone pairs. I'm connected to 4 things. The base shape is a tetrahedral. But with 2 lone pairs, whoop, whoop, the name of this will be a bent molecule. Carbon tetrachloride, carbon in the middle. 1, 2, 3, 4 things attached with no lone pairs means that these 2 will be the same, and 4 things is called a tetrahedral. So there you go. There's how you do the back. The substitute will have the answer key, but I want to do this one because this one is a triple bond and that's a little bit different. So the center, let's say that the center of this molecule is carbon, and we're trying to figure out how many connections it has. We're only worried about the carbon and what the carbon is connected to. It's connected to a hydrogen, so we've got this bond here and the nitrogen over here. Now, even though that's a triple bond, we're still only going to count this as 1, 2 things that it's attached to. 1, 2, hydrogen, nitrogen. When it's connected to 2 things, it is linear. Since the carbon doesn't have any lone pairs, it will have the same geometry. So don't worry too much about if it's a triple bond or anything. It's just how many things is it connected to. The carbon is connected to 1, 2. All right, check your answers with the sub, and then we're done with this homework.